what is this session about? My first two notes, they're just kind of general supervised learning, right? So you saw a lot of the math. Now I want to see, how can you turn some of that math into solving real world data analysis problems or machine problems? In the process, we'll see a few different kinds of model classes. We'll see regression, we'll see classification, we'll see how to work with many features, we'll see how to work with trees. We'll discuss some of the practical aspects of pre-processing, right? Because it's one thing to know a bunch of models, it's another thing to be able to adapt to your data so that the models are actually effective on that data. From there, we're going to talk a little bit about model evaluation. This is kind of a lot of machine learning isn't just coming up with new algorithms, but it's being able to tell how have I tuned it properly? Because sometimes there's so many choices that having a systematic way to actually decide on how to select the optimal model, that can be a really tricky thing. So we'll discuss that. And at the very end, if we have time, we'll think a little bit about how do you visualize the output of a model? How do you criticize it? How do you communicate it? Because in real problems, it's not enough to just fit a model and call it a day. Right? You need to be able to fit a model and then understand how do you integrate it into kind of workflows for people who don't already speak machine learning. Right? So that's going to be the final part. So hoping you can get some useful examples and just some pictures and some basic code for how to do each of these steps. Okay. So it's tricky how to introduce prediction, right? I sometimes feel like the human mind is almost like a prediction machine, right? Sometimes we're just making predictions of things without even realizing it, right? So here's a kind of a silly example, but it's something I think about because I have to take the bus in Madison, and Madison doesn't have the best bus system. So I'm often waiting like 10, 15 minutes for some bus to arrive, right? And in my head, a lot of times I'm thinking, I can try to estimate just by something about my environment, about how long do I think I have to wait at this bus stop, right? So I don't know if you've ever tried something like this, right? But you can sometimes tell, like, if there are a lot of people at the bus stop, there's probably a bus coming very soon, right? Because I mean, everyone else is also waiting there. There must have been, it's late and then it's going to be arriving soon. Sometimes though, like there's no one there and then you might think, okay, I might have just missed the bus. Or maybe you can look at the traffic, or if it's like iced over and it's snowing, because that's what happens in Wisconsin, then you might know, like, okay, I might have to wait a little extra longer because everyone is running a little bit slower. Right? So in the back of kind of automatically, without even having to do any kind of computation, without having to do any math, our brains are able to just learn relevant features of certain situations and use them to make forecasts or use them to make predictions that guide any kind of downstream decision making. So it's kind of amazing that we can do that automatically. To turn it into code or to turn it into something that's a computer can understand, that's pretty tricky, right? That's what so much of statistics and machine learning is about. As a first step to being able to formalize this process, let's come up with some notation. I'm going to be using this notation kind of XY to represent features of some situation, and then the associated, what you would want to be the ideal prediction, right? So like the true response value. So maybe XI is containing a whole bunch of features about me waiting at the bus stop. So it's like the weather, it's how many people at the bus stop, it's all these different features. And then YI is the true amount of time it took me to wait. And maybe I've collected a year's worth of data. I've just waited at the bus stop for every day for a year, and now I have a whole bunch of variable relationships between all these predictors and the true response. Now the question is, can I now build a model so that I don't need to guess in my mind, I can actually give it to the computer and the computer can make a prediction. That's the task. Okay, some more terminology. Often hear people talk about regression and classification. Regression refers to the situation where the response variable is continuous. Classification, you expect the response to be categorical. So there's only a few discrete values that it could take on. Okay, so here's an example. Maybe you are treating a patient and maybe they have had some partial success at the beginning of the treatment, but you worry that maybe the disease will recur. This is a binary yes or no decision question. Like, is the disease going to recur or not? So that, since it's binary, only discrete responses, is a classification problem. It's a different problem. Maybe you're looking at a whole bunch of satellite imagery. You're trying to decide how much crop yield did this farm have that's in this satellite image. This is a regression problem. Right? It's not yes, it had yield or no. It's actually like it had a little bit of yield. You know, it had 100 units, 200 units, 1,000 units. You can actually make those quantitative comparisons. So that's a regression. Okay, so that's terminology. To link it back to math, right? Everything that you've been seeing before, the key link is really geometrical. So now that we have these notation, now that we have this abstraction, we can come up with a geometric representation of the prediction problem. So for regression, you can think of it as the observed data are all these little points. And you need to learn the general underlying law that relates these predictors to the response that you're trying to predict. You only have noisy observations. That's why the points don't lie exactly on the line. There's a little bit of error caused by other factors that you can't control. But then you can discern a general kind of trend, and you would like to be able to learn that. So this is the one-dimensional picture. We could easily do this in 2 dimensions. It becomes this sort of surface. Right, so here I have 2 predictors. It's the number of people who are waiting at the stop and also the amount of traffic. Both of these influence the true waiting time. And then you can try, the data are lying in 3D in some space, and you can try to fit the curve that will be well approximating these data. So we've turned in this kind of informal, intuitive process that's going on in the brain into a formal mathematical geometrical. That's regression. What about classification? So classification, we can no longer draw these curves and surfaces because the response only takes on a couple of discrete values. But I find it useful to think about assigning each of the classes a different color, right? And then thinking about how do the colors separate as a function of the different features. So we're thinking about the recovery or not recovery for the disease example. So maybe one of the features is the blood pressure. And maybe people with lower blood pressure tend to recover, and then people with higher blood pressure tend not to. It's not a perfect predictor, right? Sometimes, people recover even with higher blood pressure, but then it seems to separate the groups pretty well. So again, this is geometry. You can try to find a point on this line that separates the groups. This is just in 1D, but the same idea applies in several dimensions. Right? So here is 2D. The goal of all this analysis is going to be, can you learn a curve which separates the colors? Right? And then that curve you will use on all future examples. So even though you only train on some, maybe like 100 examples, you can then use whatever model you've trained there and you can apply it to all the new patients who've come in. Right? So that's pretty neat. You can kind of automate that whole decision-making process. Okay. If anyone has questions, feel free to leave it in the chat. I'll keep an eye out. Yeah, maybe I'll pause for any questions, and then we'll move to model classes. Okay, I think this might be a review. So let's move on. Okay, so calling machine learning, we have one question. Okay, so elaborating on regression and classification. So yeah, I would just try to internalize it as having different, like regression is always going to be the sort of curve situation where like this, right? This is why. Regression, you're always going to have a whole bunch of x's. These are your predictors. Y is some response, and it's a continuous response. So like wait time can be any of these continuous values, right? And same with the farming example, right? So for the farming example, you might do something like, like height of crops, and then crop yield, right? So you might be thinking like if the plants look really big, right, then there's probably higher crop yield. And since crop yield can be any continuous value, we're going to call that a regression problem. But then the problem, like the disease classification, this doesn't have that property. It's either yes or no. It can be like class A, class B, class C. Well, any other questions? It's good to take time. Okay, so let's move on to model classes. So this is the idea. So yeah, I sometimes feel like when I say that regression and classification are geometrical problems, or that they're like curve fitting, some people get offended when I say this, right? Because they're like, no, like how can it just be curve fitting? Curve fitting sounds so simple. It should be something about, psychology or neuroscience, and there's something very deep about it. But my response to that is always like, drawing curves, especially curves when you have many features, this is a really complicated problem. Right? Geometry is not simple. Just because it doesn't mean it's easy, right? So like what we're going to have to do is we're going to have some sort of systematic way of choosing a whole bunch of possible curves. And we're going to review three main classes. So they're going to be linear models, sparse linear models, and tree-based methods. Between these three, you have most of classical machine learning. In the later today, you're going to be talking about deep learning, which is kind of like another one of these major topics. Right? But then before deep learning, these were some of the most standard approaches. Okay. They're still useful in a lot of situations. So first, what is a linear model? First, let's think about a linear model where you have exactly one predictor. So if you have exactly one predictor, imagine it's the number of people at the stop. Remember, the more people at the stop, the more likely the bus is about to just arrive. So you have to wait less. This sort of negative slope between wait time and the number of people at the stop. The way you can parameterize a straight line through this data is you have to define the intercept, and then you have to define the slope. In this equation here, B0 is the intercept. This is intercept. B1 is the slope. So here, B1 is some negative number. Maybe this equation is like, if there's no one at the bus stop, maybe I have to wait 20 minutes. And then with each additional person, maybe it decreases by 2 minutes, right? Times the number of people. So that's just my equation for predicting how long I'm going to have to wait at the bus stop. Just one predictor. Okay, so that's convenient if you only have one. We can visualize it very easily. But what if we have many? Question. Okay, so what if we have many? The idea is to kind of have the same relationship and then add them all together across many different features, right? So instead of just B0 plus B1 x1, that's just one feature. You could do the same and then plus a B2 x2, that's for a second feature, B3 x3, and so on, right? So This is allowing you now to incorporate some information from all the possible features. So you say it's not just the number of people, right? Like every additional person, I subtract 2 minutes of my wait time. But I might also say something like the traffic level. So if the traffic level is like 2 cars passing every 30 seconds, that's not very bad. So then I would think that things are probably moving really fast, right? So I might have something where it's like plus 3 minutes per additional car in traffic. Okay, and then you can keep on incorporating new features like this to build some new equation. And that is this linear regression equation with multiple features. I will be using this notation a little bit, even though it's not super important if you haven't seen it before. It's just slightly easier than writing out the whole summation. This is called a dot product. It comes up a lot in linear algebra. Okay, so this is just geometrical representation of having several features at once. So you have an intercept still, that's this B0, but now you have some influence from the predictor for one of the features. This is the first feature's influence. And then you have some influence from the second feature, that's B2. So B1 is summarizing influence from one feature, B2 is influence from the other feature. Okay, so this gives us a way of drawing these planes in kind of arbitrary dimensions. So I drew it in 1 dimension and 2 dimension, but you could work with as many features as you want. And now we can draw planes in d dimensions. The question is, you have a data set, like we had promised some approach of automating the search across all the possible curves. Right? We still have many potential lines that we could be drawing. So how do we pick a good line? Right? So this is the question. Didn't render. This summation is for everything. Okay. Yeah, the question is like, I have data like this. In theory, I could always draw this curve and say I've learned a decision rule between my predictor and the response. But this is a very bad decision rule. It barely tracks the truth. Right? But then our model class has so much flexibility, right? This has some intercept and some slope. This is a different intercept, a different slope. This is a better intercept and a better slope because it goes straight through the data. Right? So somehow we need to narrow it down from this infinite set of possible lines down to the line that's really actually going to go through our data. Right? So how do we choose this kind of best line? So these are the coefficients B, right? So B0, B1, B2. We need to figure out these coefficients B so that it's going to go through the data. And then what we're going to often use is this squared error loss function. I think this is probably reviewed from the previous lecture, but what is going on is this X transpose beta, that is your prediction according to your prediction rule, right? So you can imagine, right? I'll try to. Like you can imagine having some data like this. And then one of your prediction rules looks like this. The way that you say that this is a bad prediction rule is you calculate the vertical distance between the prediction rule and the true value. So you can sum up those distances and then we square them so that everything's positive. Right? And once you've squared them, you have a whole bunch of positive distances squared. You can say like if it's good or bad, because here it looks like the distances squared, they're going to be really large because you have a few really big errors. Right? Versus if I had instead fit the line, if I had fit this line, right? Then my errors aren't so bad, right? Maybe I'm a little bit off for some of them. But if you sum up all those squared distances, it's still a really small number, right? So this is how we guide our search over that infinite collection of lines. We're going to find the particular line which minimizes this criteria. This is called the least squares fit. Okay. So now let's think about classification. I can no longer think in terms of vertical distances, right? Because in classification, you only have two values it could have. There's no continuous variation in the response. So how do you measure the quality of these different classifications? Intuitively, you would try to find a line where the number of errors, right, the number of class 1, which is on one side, sorry, maybe the way to say it is like, you kind of want each side to be very pure of a certain class, right? You don't want a lot of mixing in the classes across the two groups, right? Like if I had drawn a decision rule like this is a really bad decision rule because I have a whole bunch of red points here. I also have a whole bunch of red points here, right? And it seems like there's actually no discrimination between the two classes coming from this choice of line. So we need to be able to measure this. You could just look at the misclassification rate, but a more subtle way is to use something called a binary cross entropy. Okay, but sorry, I'm getting a little bit ahead of myself. So first, we need to know how to define all the different lines, all the different decision rules. Okay. So how can you think about a line in this 2D space? You can think of it as you can translate it and you can rotate it. So the main idea is going to be, you have to kind of pick some anchor point. So like here's some anchor, and then you have to pick a direction. And once you've picked the anchor and the direction, then you can define the decision as the plane that's perpendicular to it. Right. If I had picked this anchor point and that orientation, then it would have defined a different one. It would have defined this one. And then I would be splitting my data into, this is one class and then the other side is another class. But the main idea is no matter what kind of linear decision boundary I want, I can always get it by first defining these arrows and then looking at the line that's perpendicular to that arrow and kind of touching it at the base. And that's exactly what this formula does. This is not obvious, right? But then it's exactly what it does, because kind of any direction that's perpendicular to B, so any change that's perpendicular to B, by definition of perpendicularity, these inner products are 0. So what it means is that it's going to be a constant value on any line that's perpendicular to the arrow. And that's why the decision rule is always going to be a line perpendicular to the arrow B. It's not super important. And the more important point is that with different choices of B, you get these different points, or you get these different decision boundaries. Okay, so that's defining this whole infinite collection of decision boundaries. Now we need to figure out how to actually pick one of them. And this is this cross entropy function. Okay, what is this doing? So think of what happens if f sub b is, imagine it's the probability of a certain class, right? So we have the red class and the purple class. So imagine that we're trying to get the probability of being in the red class. And that's what f sub b is, giving us the probability of being in the red class. Okay. Let's say it's, let's say like yi is actually like red class. And then f sub b is like actually, It's actually 1. And which we're going to think is red class. This is the best possible situation, right? It's a good situation because you are guessing the correct class and you're guessing it with really high probability, or like the highest possible probability, right? And if you look at the terms, like everything will now be 0, right? Because log 1 is going to be 0. So the first term vanishes, and then you can do the same in the other term. So yeah, this is kind of the best that you can hope for. And what's nice is that this is going to measure, it's also going to measure if you're very far off, right? Like what if you had been very confident in the wrong thing? So the picture you can have in mind is this one. So if you are correct about the class, right, then you get no penalty at all. You're fine. But then if you're actually a little bit, here it's like you're actually still correct about the class, but you're not as confident as you should be. So you get a little bit of penalty, right? And then there's this worse and worse regime where you are, really confident about the wrong class. And that's when you start getting these very bad penalties. So yeah, that's if you just plot the terms in the cross entropy function, that's what it's going to be able to tell you. It's going to be able to tell you, are you in the right ballpark, or are you confident and totally wrong, right? And every time you're confident and wrong, it's going to penalize you a lot. Every time you're correct but not as confident as you should be, you're also going to get some penalty, but not as much as the first case. Okay. So that's hopefully enough for theory. Let's look at some code. So I want to make sure that by the end of the session, you have some idea how you actually fit this in practical data analysis, right? So I'm going to open this in my RStudio. You can also follow along in the binder notebook. Okay, let's set everything up. So we just finished this cross entropy. Okay, so first I'm going to fit a linear regression. So not classification, just regression. What this code is doing is it's using the scikit-learn package and loading a data set about diabetes. So the response value is disease severity 1 year after diagnosis. We have 10 predictors. These are in X. And then we have this severity score, which is in Y. And these are the data. Everything's already been kind of standardized and cleaned up. These are like the severity scores. So the question is, we have this X. It's 442 examples with 10 features. Each of them labeled with a Y. We need to fit regression. How to do it? Okay. You can use this linear model class in scikit-learn. So I made the import before. Right, I imported datasets. I also imported linear model. This line just initializes the model. It says, consider any linear curve. I'm not going to be picky about which one you choose. Just I want to have the option of choosing any linear curve. That's what this first line is saying. The second one is saying, okay, now based on the data, compute the squared error losses and find me the best possible curve. Right. And it does the optimization internally before we even notice. And I'll just run that. Once you get it, model.coef, these are the B. These are the fitted parameters of the regression equation. It determines where the line goes. Okay, and here are the coefficients. So you can just print it out. Okay. I'm going to do the same thing with penguin, or classification data set on penguins. I think this is a cute little example. Okay, so the problem is there are 3 kinds of penguins. They look slightly different from one another. we have a bunch of features about them, and we want to be able to classify which species is which. Actually, I wonder, you can, if you click on the link, you'll be able to see pictures of the actual penguins. They're kind of cute. But then some of the features we have like the depth of the bill, how long it is. You also have something about the flippers. So we're going to have to try to figure out which penguin is which just from these features. Okay, so I posted the data at this link. You can read it in. You get the species of penguin in the first column. I have some information about which island it is. We're not going to use the island information. We're also not going to use the sex or year of the observation, but we will use all these kind of body measurement characteristics. So bill length, body mass, things like that. Okay, actually first, we're going to just use bill length and depth. So it's these things. And we're going to try to use that to predict which penguin it is. Before you ever fit a model, it's often helpful to just make a plot, right? Just, is it possible to make this prediction just by eye, looking at the data? If you can make it by eye, then there's a pretty good chance that your model is going to be able to imitate that. If even you have trouble making the classification, then you should kind of slow down and see, is there any way you can collect better data or more discriminating data? But for now, let's just look at the plot. I'm using a package in R called ggplot. I feel like ggplot is its own course. I have some materials on my website if you want to learn a little bit more about it. If you go to Stat 479, it's a data visualization class, and I have a whole bunch of lectures on ggplot and their recordings and everything if you care to follow. For now, just ignore it. What I really want you to pay attention, let's look at the data, right? So here, each point is a different penguin. We have these two features. We have three kinds of penguin shaded different colors. And what's really nice is that we can really clearly see the separation in the penguins based on these two features. Right? Seems like the Adelie penguin have relatively short beaks, right? The Gen 2 penguins have smaller depth compared to the chin strap penguins, but then they have about the same bill length, right? So it looks like we might be able to try separating these groups. Now there's a subtlety I didn't mention when I was discussing classification. When I was discussing classification, I said, just draw a line that separates the two groups. I didn't say anything about what happens if you have more than two groups though. So when you have more than two groups, it turns out that it's almost the same kind of calculations. It's just instead of one arrow that defines the decision boundary, you need a couple arrows to define the decision boundary. So for example, like in this kind of picture, it barely rendered here, but then you can kind of make out that there should be a decision rule, something like this. And then we just need to train the model to learn that sort of separation. So it's a little bit more subtle than just having a single line that separates the groups, but it's the same principle, right? Like I can have a little arrow that defines that one, and have an arrow that defines that one. I can have an arrow that defines this. Okay. So that's the data. Let's actually fit the model. The way you fit the model, pretty similar. So instead of defining a linear regression class, I define a logistic regression class. Notice if you went back to the original data, there were a few missing values. I don't know if you caught that when I thought of it. Let's just set. Let's see. Yeah, so there were a couple, like this row 4 has a missing value for bill length. These methods are not going to be able to work with missing values right out of the box, so I'm going to drop them first. That's what drop NA does, removes the missing values. Now I have X and Y. These are my two predictors that I made the plot from and the color species. Fit is going to try to minimize this cross entropy loss, try to find a decision rule which is going to be pretty good across all the classes, minimize the number of misclassifications. And then at the end, I'm just storing all the predicted values in some new column of the penguins dataset. The Y hat column is just the predicted class based on all the data. No. Okay. And no, at this point, we can go back. Actually, I think. Okay, so what am I plotting here? So here, each panel is a predicted class. So it does seem like it kind of learned a boundary here, learned kind of boundary here, and boundary here. Okay. Okay, so it's learned this set of boundaries to distinguish between the classes. Okay. And the things, though, you can notice, there are still some false positives or like a misclassifications, right? So this penguin here, it's actually a chin strap penguin. It's a green point, but it got classified into the Adelie group, right? And same with these penguins here. So this one's an Adelie, but it got classified as chin strap, right? So what do we notice in all these examples? I'll just erase it so we can see them again. So we make a lot of misclassifications near the boundary, right? Which shouldn't be so surprising, right? These are penguins whose beaks look like they come from other species, but they are a different species. So these are the kinds of errors that you might expect. Okay. So that's basic kind of linear models and logistic regression. It should be recapped from before. But are there any questions? I'll take a pause before going to the other models. Okay. So there's a question, is the boundary always going to be linear in the case of classification? So for the model that I've described, for logistic regression, yes, it will always be linear. But in more complicated models, so we'll see tree-based models later, and definitely any kind of deep learning model that you'll see later, there will be lots of curved nonlinear boundaries. But I'll just highlight that. You notice that logistic regression is within the linear model class for scikit-learn. So it's kind of a reference to the fact that the decision boundaries for logistic regression are always linear. Any other questions? Okay, move on. So now we're going to talk about sparse linear models. So what is the idea of a sparse linear model? Okay, so imagine we have not just 2 features, but imagine we have 100 features, right? We've just recorded everything that we could possibly think could be related, but in reality, most of them are not. So in this sort of situation, a linear model can actually do very poorly, because the linear model might get very distracted trying to figure out how to get irrelevant features related to the response, even though there's no way to make them related. So what you kind of want to encourage in that situation is you want to make many of the coefficients exactly 0. You want to tell explicitly, like, this feature does not matter for this classification, or this feature does not matter for this regression. So that's what a sparse linear model does. And it turns out if you kind of force that sort of sparsity in the coefficient, you can stabilize your regression a lot, and you can end up often getting better performance in this sort of many feature regime than you would get if you actually tried using a full linear model. It's a little bit counterintuitive. It looks like you're throwing information away. It looks like you're ignoring data. But it turns out the benefit of focusing your attention on a few good features far outweighs the loss you get by ignoring a bunch of them that are probably not relevant. Okay, geometrically, what's going on is you have a few features that are relevant. So this is like relevant feature, and here is like an irrelevant And for those irrelevant features, you want the slope to be 0. You want B0 to be exactly 0. So it means that feature has no contribution. Okay. So I drew it for regression first, but then the same idea applies to classification. So in the classification situation, what it means is that your decision boundary, it ignores some of the features, right? So like in this example, it pays a lot of attention to current blood pressure, but is completely ignoring resting heart rate, right? Having a high resting heart rate versus a low resting heart rate, it doesn't change the decision boundary, right? The only thing that matters is current blood pressure. So if you're looking at these sort of axis-aligned decision boundaries, you're in the sparse regime. Okay, so sparsity. Let's look at a code example. So again, this is hosted on this Box link. I don't know if you all might be too young to watch The Office. The Office was a comedy TV show that was popular when I was in high school and college. And oh wait, question. Oh, I'll zoom out next one. Okay. Yeah, The Office TV show. It's pretty funny, I guess. I'm not that familiar. But then what this data set is, it has the number of times each actor appeared in each of the episodes and also who wrote the episode. And so we can look at X. Or actually, I think I probably printed out here. Yeah, so it's like season 1, episode 1. How many times did Andy show up? Andy did not show up at all, right? But then it does this for every single actor and every of the writers as well. And then you have the rating of that episode. So the first episode of The Office on IMDb has a rating of 7.6. And you can do this for every single episode. So we have this big data set. I don't know what it is. We have 136, right? 136 episodes, 28 actors and writers. We want to see, are any of them maybe predictive of the rating? Right? Maybe when some of the actors on, it's just like really funny, and then we're gonna get a really high rating, and then some of the writers just kind of consistently ruining the show. Who knows, right? That's the question. Okay, how do you fit it? So we're gonna now use the elastic net. So elastic net is an example of these sparse linear models. So these parameters are controlling the amount of sparsity. Right? You can either tell the model, I want you to ignore all but the most important features, or you can be a little bit more lenient and say, okay, ignore some of the features, but keep most of them in. Right? So that's a hyperparameter. You have to choose that. When we get into cross-validation and testing, we'll see that in a little bit more detail. But for now, let's just say, I'll pick some hyperparameter and we'll just see what happens when we use sparse linear regression. Kind of one of the nice things about scikit-learn is that once you define the model, almost all the other code is exactly the same across all the models, right? So this .fit xy, .predict x, we've seen this 3 times already. So nothing that's surprising here. But the thing that's kind of interesting is once I fit it and I look at the coefficient, right? So some of the coefficients non-zero, but a lot of the coefficients are exactly 0. And this is really convenient for interpretation because it says, if you really want to predict the IMDb rating, you don't actually need to pay attention to these actors at all. They're not important. The only actors you really need to pay attention to are these actors, right? And probably the ones with the larger coefficients, or the ones that are larger in magnitude. Those are the ones that are more interesting. Okay, yeah, so let's out again. So that's the data. That's how you get logistic regression for sparse linear regression. Another question. Is sparse linear model somewhat related to removing outliers during data preprocessing? Not really, actually, right? Because the thing is, like having an outlier can actually fool a sparse linear regression model completely, right? So the picture could be like, there is no relationship between this variable and the response, except you have this one outlier for some random reason that's like that. Right? Now, ideally, you would want the coefficient to be 0 here too. But then sparse linear regression is still going to try fitting, that outlier because it still needs to minimize at least squares like criteria. So it doesn't necessarily guard you against any of these kind of outlier issues. There is a sense in which kind of this sort of these sort of penalties do show up. Like if the penalties that create sparsity are somehow related to being resistant to outliers, but it's a very subtle connection and it's not directly related to sparse linear models. Oh. So there's a question about cross entropy loss. Yeah. Yeah, that is the correct interpretation. And it does have implication for what the model learns. In a way, it almost makes the model want to be as confident as possible. Right? It tries to get the probabilities as close to 0 and 1 as possible without making too many mistakes. So it's not enough for the model to get it right, but with a probability that says 0.51 for one class and 0.49 for the other, right? It actually is penalized for being too underconfident. Okay. This last picture, I just wanted to show you can plot here is y versus y hat. So it's the true IMDb rating versus the predicted according to the sparse linear model. You know, it's correlated. It's not super correlated, but there's a lot of noise, right? There are a lot of factors that influence the rating of a movie that aren't just like how many times was this actor mentioned, right? There's the quality of the script. There's kind of where in the season it is, what new conflict has arisen, right? These are all important features that aren't in the data set. So maybe this is already pretty good and we shouldn't get too greedy. But it's nice that there is a relationship. It's not pure noise. There is some influence between which actors and writers are appearing and what the rating of the movie is. Okay, so we're almost done with this notes. So the last section, so there was a question earlier about linearity, right? So far everything we've looked at is linear. In fact, sparse linear it's almost like less than linear, right? Because a lot of the coefficients can't have any influence at all. Tree-based models, these are very nonlinear. And then the way that you motivate it is also very different from what we had been thinking about for other regression. Okay. So let's go back to the bus stop example, and let's think about, how might you predict it differently? One way to decide would be you could draw this sort of tree. Right? So first you could say, okay, is it a weekend or not? Because usually on the weekend it takes longer for the bus to arrive, right? And then you can say, okay, no, it's not the weekend. And then you can ask, wait, is it raining or not? Like when it's raining, that usually makes the bus take longer too. Right? And you can keep on doing this process a few times until you get into an area where it's, once I've narrowed it down to this kind of environment, then the amount of time I expect is usually pretty narrow, right? And that can be your decision rule. So basically like march down the tree and then get to the leaf and pick whatever is the average for all the examples that you have at that leaf. So here's saying that this kind of no traffic, no rain situation is really fast. And then the like high traffic weekend situation is very slow. And it works for both regression and classification, right? So for regression, you would take like a continuous value at the leaf. For classification, you would say, I think this patient's going to recover based on the tree kind of decisions. Or you can say, I don't think this patient will recover based on this characteristics in the tree. So you can do both regression and classification with this. Now, I told you in the beginning that regression classification, they're just drawing curves in data. This does not look at all like a curve in data. So what's the connection? How is this actually a curve? It turns out that it is, but it takes a little bit of thinking. So first imagine, just split it according to one variable. Right? Split it according to traffic, less than 0.9, bigger than 0.9. Right? Look at all the examples of having to wait in less than 0.9 traffic, and then all the example waiting in more than 0.9 traffic, and look at how long it took. Then you get some numbers, so 10 minutes and 30 minutes. So high traffic, long wait. it actually, that tree, that like tiny little tree, corresponds to this sort of picture geometrically. So it says up till 0.9 in traffic, I always predict 10 minutes. It doesn't matter whether it's 0.8 or 0.0. Right? But then larger than 0.9, I'm always going to predict 30 minutes. That's the connection. That's how you go from these trees to this curve. It's not really a smooth curve. It's like a very sharp one, but it's still, you know, a curve in the mathematical sense. Okay. Now, what about more complicated splits? More complicated splits are actually drawing partitions. This is not obvious, but we can think of it step by step. So, you know, traffic, and rain. So let's do the first step on this tree. The first step is saying rain less than 1 or rain bigger than 1. So I find 1 on my diagram and I split it at less than 1 or bigger than 1. Right? Then for the rain larger than 1, actually no, I'll do traffic first. So I've just made this split. Now I'm going to consider this split. So among rain less than 1, I'm going to look at traffic less than 0.2 and traffic larger than 0.2. And so I'm going to say this is 0.2, and I've split it again now for this region that's less than 1 for rain. And then I have numbers, right? So if it was rain less than 1 and traffic less than 0.2, that's a 4 minutes, and then the one is 6 minutes. Right? And you can continue doing this on the other side of the tree, right? So for rain less than 0.2 or rain less than 2 or not, I just draw 2, and then it's either less than 2 or not. So here, if it's bigger than 1 and less than 2, it's 14. And if it's bigger than 1 and bigger than 2, 30. So that's how I got this diagram. You just go down the tree, and then each time you split it. Okay, so that's an individual tree. It turns out that prediction rules based on individual trees don't work that well, but it's possible to try training a whole collection of trees. The details are a little bit beyond these notes, but then this is the main idea behind random forest and gradient boosting machines. It's just try to subsample your data in a clever way, or try to learn a sequence of kind of examples that are hard in different ways, and then take all those different trees and then average the tree. Right? So what's going on is like one of the trees gave you a decision rule that looks like this. Right? Maybe another of the trees gave you a decision rule that looks like this, and then another like this. But they're all kind of going down and around this area. You can imagine then averaging all these predictions. Right? And when you average the predictions, it kind of smooths it out a little bit. So maybe you get something more like this. That's what random forests are doing. They're taking all those sharp split kind of trees and they're smoothing it out. And that's how I can achieve nonlinear. How to do this in Python? So we're going to use this gradient boosting tree classifier and regressor. Okay, yeah, so we're going to look at the penguin data set again. So classifier. Okay, that trained it. And then I also got a column with the predictions. This is the exact same code as before. The only difference is I used a gradient boosting classifier instead of a logistic regression classifier. Okay, you get predictions, and then I can plot again across the 3 classes, and I can see what was the true species. And it actually makes no training errors. Right, so even those examples along the boundary, which logistic regression messed up, this is able to kind of draw neatly around those kind of non-linear little pieces, and it's able to get perfect training error. This does not mean it's going to have perfect test error, or doesn't mean it's like given a new penguin, it's always going to be correct. Right? But at least it's a very rich class of models you can get perfect training error. Okay. So this has been a lot. I wanted to summarize the main ideas from this set of notes. And this is the most involved set of notes. Right? So we covered 3 main model classes, the linear ones, the sparse linear ones, and the tree-based ones. How do you know when to use which? It's a big question. So think of linear and logistic regression as giving you a kind of baseline. Right? When you don't have too many features, when you want to run something really quickly, use linear or logistic regression. the color, I'm coloring it according to whether it can be used for regression or classification. So blue means you can use it for regression. Red means you can use it for classification. Purple means you can use it either regression or classification. So baseline linear methods. If you have a lot of features, so you've collected lots and lots of potentially predictive things, you can do either sparse linear or tree-based methods. The sparse linear or logistic kind of method, they do really well when you have lots and lots of irrelevant features. Random forest and gradient boosting will often do well in that situation, but not quite as well. Right? They're not as good at completely ignoring irrelevant features. But then the trade-off is sparse linear, sparse logistic, they aren't good at fitting nonlinear pattern, but then the tree-based methods will automatically be able to learn nonlinear curves or nonlinear decision boundaries. Okay, and then I have a little table about, these are fast, they're pretty interpretable. Tree-based can be a little bit slower, be a little bit harder to interpret. I have an exercise here and I gave some answers, but I think let's actually take 10 minutes. I want everyone to try this exercise on the Google Doc. Okay, so let's do exercise 1. If you are in person, split into groups of like 2 or 3. If you're online, send a message in the channel for this session saying that you want a partner, and then message someone who said they want a partner. So what happened here? Yeah, somehow I got. Okay. What this exercise is you have to pretend to be either like a real scientist or engineer or even like business or social scientist, right? Someone who knows a lot about some problem, but doesn't know any machine learning. And then I want someone else in the group to be someone who's like a machine learning expert. And I want you to try to say, pretend that you're consulting for this client, right? You have to describe like, what is the problem? What are you trying to predict? Why is it important that you be able to predict that? What are the features that are available for prediction? Right? Is it a regression problem or is it a classification problem? And then kind of what is the initial approach? Would you recommend an initial linear approach? Would you recommend an initial tree-based approach? So yeah, let's take 10 minutes to do this. And then just write your answers in here. Okay. And if there are any questions, I can reply on the Discord. Okay. Well, I don't see any responses. If you have time just to write it up later, I would really appreciate it. I think it would be nice to have a record of the discussion. But I also realize doing everything hybrid is a little bit tricky. It would be nicer if there were just worksheets. But that's okay. We have 5 minutes before our next break, but it should be enough time to at least introduce the next set of topics. Right. So in the next set of topics, we're going to be talking a little bit about preprocessing and featureization. Right. So this is one of these areas that's not very glamorous. It's not something that you see a lot of people publishing papers about. It's actually really, really important. And I'll just throw in like the research that I do see in this area is often really, really interesting. Right. So the question is, when you are trying to solve some data analysis or machine learning modeling problem, where should you invest your effort? Should you invest your effort tuning the parameters of some model you have? Should you invest your effort evaluating the data set and looking for errors, looking for ways to clean it up? I would argue that the second is a much better use of time in most problems, right? Only in certain very highly refined pipelines where everyone's studied the data for so many years that there's nothing wrong with it, then okay, you can focus on the model. But a lot of real problems, when you're just starting collecting things, there's always going to be some issues. Right. Okay. But then I should have the caveat is never overwrite the raw data. This is critically important, right? I've seen this happen, right? Where it's like, oh, I have the raw data. Kris has told me to pre-process the data. So I'm going to just go in Excel and change entries in the raw data. You should never do this. The reason is because it's not reproducible, in one issue. And also it makes it impossible to compare different ways of pre-processing data. If you have a script that's able to take the raw data and produce different versions of the pre-processed data, right? So maybe there are different ways that you could pre-process and you have different versions for each. If you do that, you'll be able to actually tell a certain kind of pre-processing really helped performance of my model. Other kind of pre-processing was not necessary, or maybe it hurt the performance of the model, right? But you will never know that if you hard-coded everything and you lost the raw data. Okay, that's the first point. Different kinds of pre-processing. We'll discuss this in detail in a minute or in the next session. But then the main things that we're going to have to watch out for is outliers. So outliers, differences in scales, missing values. So those are going to be the, missing values, and then what to do with categorical data. And so far, everything has been numerical. I've been drawing pictures as if all the predictors are numbers. But then a lot of real data, you're going to have categorical inputs. So we're going to have to think about that. Right? Okay, so that's going to be pre-processing. Just how do you manage it? How do you even detect it? That's something to be paying attention to. And I think actually, yeah, we can talk about outliers first. This was mentioned when I was going over sparse models, right? And I drew a picture that was almost like this, right? So there's a question of like, why are outliers bad, right? It'd be nice if just all the models just worked with them. But reality is, sometimes a single observation can throw off your entire model. And that's what this picture is illustrating. Right? Since like this error is so large, it gets a huge penalty from the squared error loss. Right? So the model is actually happy to take all these errors, right, in order to have a little bit less error for that one outlier. Right? When really a much better choice would have been having it all right around there. Right? So that's why outliers are bad. A nice trick to try to detect them, there's this kind of rule based on the interquartile range. So look at the range where most of the data are, and then inflate it by 1.5 times. If you have data outside of that 1.5 times the interquartile range, those are candidates for being outliers. Once you see them, you should probably remove them, or you can truncate them. So if you have like all your data lie in a histogram like this, and then you have one observation that's way off, a natural thing, you can either remove that point or you can just truncate it to right here. And once you replace it with the next highest value, then it doesn't have a risk of contaminating the rest of the fit. Okay, we'll continue with pre-processing. I think right now is a break.